Hello and welcome to this lecture. In this lecture, we will talk about the cumulative distribution function, or quite often this word cumulative is dropped. This word is dropped. Many people will simply call it a distribution function, which is also fine. I mean, so both of them are good enough. I think traditionally many people use cumulative distribution function. I'll keep saying cumulative distribution function, but you'll see in many books people will simply call this the distribution function. It's not a bad name. Distribution function is also a very good name. One can use either of these. Okay. So here's the definition for CDF. The reason why I like CDF is CDF sounds like a much better acronym than DF. Okay, so CDF is quite nice. So the CDF of a random variable, any random variable x, okay, has a CDF, and the CDF is defined in this fashion. Okay, so it's a function from the real line to 0, 1. Okay, so fx of x is a function. The input x, small x, comes from the real line. Any real number can be its input. And the output is a value between 0 and 1. Okay, so that's what's important to know what it is. And how do we define it? How do we connect it to the random variable? Notice that notation f sub capital X of small x. Okay, so it sort of succinctly conveys everything. It's the CDF of the random variable x evaluated at small x, and that's simply defined as the probability that the random variable is less than or equal to small x. Okay, so this is the definition of the cumulative distribution function. It seems simple enough. It's easy enough to do this, right? So given any random variable, one should be able to do it. At least discrete random variables, we know how to compute the CDF. Okay, but the CDF is a very important bridge between the discrete world and the continuous world. You'll see it gives you that nice interconnect, and I'll convey that to you in this lecture or maybe the next one. Okay, but before that, let's first understand what the CDF is, do some simple calculations with it, get used to the idea of how to work with the CDF, because so far we've been working with the PMF, even with the discrete random variable, right? We've only discrete random variables so far. We've been working with PMF, and it's always probability that x equal to small x, right? So now we have the slightly unusual situation of probability of x being less than or equal to small x, but that should not really worry us too much, because it's less than or equal to small x. We know how to count and all that. So that's what we have to get used to now first, and then we'll see how this nicely generalizes beyond discrete random variables also. Okay, so let's get started. A few quick properties. These properties are very easy to prove. The first one is, if you want probability that x falls between a and b, okay, notice the way a and b are included here. A is not included, b is included. Okay, probability that x falls between a and b, a not included, b included, that will simply be fx of b minus fx of a. So the difference of two different values of the CDF is equal to the probability that the random variables falls within the 2 points. Okay, so it's an important thing to keep in mind. It's a very nice property. It's very easy to prove, right? So fx of b is probability that x is less than or equal to b. Fx of a is probability that x is less than or equal to a. If you subtract these two, like these two are, so you will get all the values of x which are less than or equal to b, but they are greater than a. That's exactly this case, right? So it's a very easy derivation. That's good to see. Okay. So the next important property for fx is it takes non-negative values. Clearly it takes non-negative values. It takes values between 0 and 1, right? So we've already said that's the property of fx, and it's anyway a probability. It has to be between 0 and 1. It can't do anything else. Okay. But it has to be a non-decreasing function. What is non-decreasing? It has to, it cannot slope down. It has to be, it has to sort of keep increasing. Why is that? Because if small x increases, I'm saying now probability that x is less than or equal to something larger, right? So that should be a bigger event. So once you look at a bigger event, right, the probability of it has to be bigger, right? So you go back to your basic axioms about probability. When you have a bigger event and there's a smaller event inside it, probability of the bigger event is bigger. Okay, so because of that reason, fx is a non-decreasing function. Okay, so now the last two properties are sort of limiting properties, in the sense that I want to look at the case where small x becomes smaller and smaller and smaller and keeps on going in the minus infinity direction. So eventually, whatever your random variable is, if your small x is going towards the left, eventually you will run out of all the possible values it can take, right? So your probability will go to 0, so fx will go to 0. So it starts at 0 at minus infinity, And notice what happens at plus infinity. If you keep moving off to the right, you will, when you just by saying x is less than or equal to infinity, you are including all the possible values that x can take. So that probability is simply 1. Okay. So immediately picture this random variable, this function. It starts at 0. It has to keep on increasing, cannot decrease. It takes values between 0 and 1. At infinity, it goes to 1. So it will have always a picture like that. So any CDF will be like that. It will start at 0, maybe it will do some things, and then eventually it will go to 1. Okay, we don't know what's going to happen in the middle, but eventually that's what will happen. It starts at 0, goes to 1, and the important property, like I said, is difference between two values of the CDF is simply the probability that x lies in that range. There are some adjustments for the beginning, end, etc., but that's what it is. Okay, simple definition, right? Distribution function, cumulative distribution function is a very important definition. Like I said, it's a bridge quite often between the discrete world and the continuous world. Okay, let's start with examples, right? So it's good to define things, but only when we do simple examples do we really understand what it is. Okay, so here's the simplest random variable that we can think of, the Bernoulli random variable x taking 0 with probability 1 minus p and 1 with probability p. Okay, and here is a picture of the CDF of this. Okay, so this is a picture of fx of x, and so notice what I've done here. Maybe the expression is easy to deal with also in this case. Now fx of x will be 0 for x less than 0. Okay, so you can see that why, right? So maybe I'll write it down. So if you say, for instance, fx of minus 1, its probability that x is less than or equal to minus 1, and clearly this is 0, right? So because x takes values only 0 and 1, okay, there's no question of this being less than or equal to minus 1, right? So for any x less than 0, fx of x equals 0, probability that x is less than or equal to 0, okay? Now if your x bit happens to be between 0 and 1, 0 inclusive, okay, then you will get 1 minus p. Why is that? So if you have fx of x and x is say between x is let's say 0.1 or something, then that's probability that x is less than or equal to 0.1, and that is probability of x equal to 0, right? So you get 1 minus p. So this is true for any other value of x between any x such that 0 is less than or equal to x less than 1. So this less than 1 is important. You cannot make it 1. Okay. Why is that? So once x becomes 1, the whole probability will be 1. Why? Because probability that x is less than or equal to 1, x includes everything, right? So that's 0 and 1, everything is included, so you get 1. Okay. So you see, you can easily check these three properties, and that's how it is. Okay. So I've just showed you some illustrations just to argue why this is true, but you can hopefully see why this CDF comes out to be 0, 1 minus p and 1. Okay. So here we took a discrete random variable x, and then we tried to compute the CDF. A much better way to visualize this is through a graph. Okay. So here is x, and here is fx of x. Okay. For x less than 0, the CDF is 0. Okay, you can see here it's 0. And I put this circle here without filling, which means at x equal to 0, the CDF is not 0, it is actually 1. Okay, so I put a solid circle here to show that it's actually, 1 minus p, which is, I don't know, some value 0.4. Okay, so this is basically 1 minus p. Okay, all right. And notice what happens between 0 and 1, fx of x stays there. It doesn't go up or it doesn't move anywhere, it just stays flat there, okay, till it hits the next point 1 where x takes some value with some probability. Okay, there again at 1 you have a discontinuity, right? You have a jump. Okay, at 1 the actual value of fx of x becomes 1, and then after 1 it just simply stays at 1. Okay, so this is the plot of this fx of x. I've just carried over the same plot. For x less than 0 it is 0, x between 0 and 1 it is 1, x greater than 1 it is 1. I'm sorry, I said that wrong. For x less than 0 it is 0. For x between 0 and 1 it is 1 minus p, and that 1 minus p comes here, it's flat. Between 0 and 1 it's flat again. And for x greater than 1, fx of x becomes equal to 1, and that's a flat line there. Okay. Now you have this filled circle and open circle here. Think about why that happens. See, at x equal to 0, there seems to be two values here, right? So I have to tell you which is the correct value for fx of x, and looking at this very closely, you say at 0 fx of x becomes 1 minus p. So you should put a solid circle on top and a unfilled circle, open circle sort of in the bottom. Same thing at x equal to 1. When x is 1, fx of x is equal to 1. Okay, so it's not 1 minus p. So at 1 minus p you put a open circle, and at 1 you put a solid circle. So it's just a figure to illustrate how the function fx of x looks. Okay, so this picture is very nice to keep in mind. If you forget about everything else, somebody gave you this picture, you learn a lot about the random variable, right? If looking at this picture, I know that the random variable is discrete. It takes two values. It takes a value 0, it takes a value 1, right? At 0, it takes that value 0 with probability 1 minus p. It takes the value 1 with probability p, right? This distance is p, this distance is 1 minus p. Okay, the jump, the amount of jump that you have in the step is equal to the probability with which x takes that value, isn't it? So for discrete random variables, the CDF sort of looks like a step, okay, and keeps going up, all right. This does not happen just for the Bernoulli random variable. I showed you in detail for the Bernoulli random variable how this plot comes, okay. You can quickly generalize this to other random variables. So let's take throwing a die as the next random variable. Now x is uniform now between 1 to 6, 1, 2, 3, 4, 5, 6. And if you do a CDF for this now, okay, I have written down the whole formula here in gory detail. It's 0 for x less than 1. It is 1 for x greater than or equal to 6, right? So that's seen. Then between, now if x is between 1 and 2, the probability that capital X is less than or equal to some value between 1 and 2, it's the same as the probability that x takes value 1, that's 1 by 6. If x is between 2 and 3, then x could be 1 or 2, so that's 2 by 6. If x is between 3 and 4, x could be, if small x is between 3 and 4, then capital X, right? So capital X could be 0, not 0, 1 or 2 or 3, and that is 3 by 6, right? So this gives you 3 by 6. It's easy to see how, so you go from small x to the possible values that capital X could take, right? So probability that capital X is less than or equal to small x is what you're doing. You just go to the possible values there and you do it. So it's quite simple enough in that case. Now you can also sketch this fx of x, which is what I've done here, and the sketch is very important. I want you to take some time and make sure you understand how this sketch came. It's very easy at some level, but sometimes if you're seeing it for the first time, it can be confusing. It's very easy, right? So on the x-axis, you go 0, 1, 2, 3, etc. For x less than 1, it is just flat at 0. For x between 1 and 2, it is flat at 1 by 6, right? So this value is 1 by 6. This value is 2 by 6, this value is 3 by 6, so on, okay. So that's what I've plotted here, okay. Just steps, and they all sort of like non-overlapping steps, and you can go from 1 up, 1 up, 1 up, starts at 0 and goes through these steps and reaches 1, okay. So this going from the PMF, right, the PMF was given to you, discrete random variables PMF was given to you, you went from PMF to the CDF, and this is the way you have to do it, okay. So supposing I give you the CDF, I want you to go back to the PMF. How will you do it? For a discrete random variable, it's very easy, isn't it? You go and identify where all the jumps happen, where all the steps happen, and how much did you jump by, okay. So you just have to say this PMF will take value 1 with probability 1 by 6, value 2 with probability 1 by 6, value 3 with probability 1 by 6, so on, okay. Wherever the jump occurred, exactly where the jump occurred, the probability of the random variable taking that value is 1 by 6. Now notice when there is no jump, if you come here for instance, let's say it's 4.5, there is no jump here, right, no jump. So that implies probability that x equals 4.5 is actually 0, isn't it? So if there is no jump, there is random variable does not take that value, as in some sense it's probability 0 of taking that value, okay. So nice simple plot. In some sense the cumulative distribution function is very nice, it's for the discrete random variable, but some of you may argue at this point the PMF is fine, PMF is good enough, why do you need the CDF, right? What did I gain from looking at the CDF? We'll come to it slowly, but at least for now try to make sure you can go from PMF to CDF, CDF to PMF for a discrete random variable. This is an important skill that you need to pick up when you deal with random variables. How do you go from PMF to CDF? How do you go from CDF to PMF for a discrete random variable? I've shown you two illustrations in simple cases. I'll also show you something slightly more general, but hopefully you see the picture. Okay. So here's a slightly more general PMF, general CDF, and let's see if we can draw some inferences from here. Here is a picture. So suppose somebody tells you that this is the picture of fx of x versus x, okay, and it's x1, x2, x3, x4, x5, p1, p2, p3, p4, p5. I've just drawn it like that. So maybe let's say, let's assume that this is in increasing order, x1, x2, x3, x4, x5, so that it's easier for us. So supposing you have to now label this axis, okay, how would you go about doing it? If this is the CDF, I've done a mistake here, let's put capital X there. If this is the CDF, how would we go about labeling this? So we know that it starts at 0 and we know it starts at, ends at 1, okay, and the PMF takes, the random variable takes value x1 with probability p1. So wherever the jump occurs, it better be x1. This jump occurs here, x2, this jump occurs here, x3, this jump occurs here, x4, and this jump occurs here, it's x5, right? So maybe I should draw dot 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 here to show where that comes from, okay? So that's easy enough to see. And then what are these jumps? What will this jump be? This jump will have a magnitude of p1, this jump will have a magnitude of p2, this jump will have a magnitude of p3, so on, right? So that's it. So CDF is very nice, right? I mean, it's easy enough to draw. It's some people may say it's a better looking picture than other things, but anyway. So you see, this is the picture of the PDF. So this kind of a picture is good to retain in your head, okay? So you have a PMF for a discrete random variable. How will the CDF look? It will start at 0 and it will jump. Wherever the random variable takes a value with positive probability, it will keep jumping. Wherever it does not take value, it will be flat, okay? So what is hidden in this is wherever it's flat, wherever the value does not have a jump, there's no jump, right? Okay, more than flat, actually there's no jump at that point, okay, that's what's very important. Whenever there's a jump exactly at that point, there is a probability of random variable taking that value. When there's no jump, it will not take that value, okay, so it's probability 0. Alright, so this is a good picture to keep in mind that hopefully nicely summarizes CDF for you, okay. It all seems simple. I've not really added anything of value beyond PMF here. It's at one level, it's another representation of the PMF if you want, but there is nice pictures you can draw which will give you an impression of where we are going, okay. So, but before that, let's do something slightly more non-trivial, okay. So, let's go to a largish random variable, okay. So far we've been dealing with, four values, 5 values, 2 values. Let's go to 100 values, okay. So, here's x, which is a random variable which takes uniform but values from 1 to 100, okay. So now trying to plot this, we'll come to plots soon enough, but let's look at the description of the CDF, okay. It takes value 0 when x is less than or equal to 0. In fact, I think this is not 0 here, this is a mistake here. This should be 1 when x is, okay, so I know what a mistake I made. This is wrong, so let me just cut this out and say if x is less than 1, that's correct, okay. So if x is less than 1, then the CDF takes value 0, okay, so that we can see easily. And then after that, you know that if x is, so if x is between 1 and 2, it takes value 1 by 100. When x is between 2 and 3, it takes value 2 by 100 and so on, right? And this is captured in this description. If k is 1, 2 to 99 and x falls between k and k plus 1 inclusive of k, not including k plus 1, then you have k by 100 for the probability, okay. And if x is greater than or equal to 100, then you go to 1, okay. So that's the picture. So there is, it starts at 0. At 1 it jumps by 0.01, 2 it jumps by 0.01, 3 it jumps by 0.01, 0.01, 0.01, 100 times it jumps and gets to 100. Okay? So it's easy to picture this, okay. So now let's start doing this calculation of probability of intervals, okay. So there's a reason why I'm doing probability of intervals here. We will quickly, in a few more slides, we will do a different way of doing this calculation. But one can ask for probabilities of intervals, right? So, a uniform random variable like this, it's easy to do the calculation. Probability that x lies between 3 and 10, okay? So, then this we know, given the way in which I have written down that interval, it's fx evaluated at 10 minus fx evaluated at 3, and you get 7 by 100. It's easy enough to see. Now, what if I change this to 3.2 to 10.6? You might say, why am I doing this? X doesn't take these values, but you'll see it's illustrative. Again, you can use the same formula, nothing changes, right? You can put capital Fx of 10.6 minus Fx of 3.2, but you know 10.6 still comes down to 10 by 100, 3.2 still comes down to 3 by 100, that's what's very important, right? So, this is 10 by 100, this is 3 by 100, interestingly this is also 10 by 100, this is also 3 by 100. Why is that? Because this whole range is just k by 100, okay. So, it does not matter whether you do 10.6, 10.2, 10.3, 10.8, you will always get 10 by 100. Does not matter if you do 3.1, 3.2, 3.3, 3.7, you will always get 3 by 100. So, you get the 7 by 100 again, okay. You can also do other ranges, like if x is less than or equal to 17, right. If you do not put anything on this side, you can take minus infinity there, and that is just fx of 17, you will get 17 by 100, right. So, this is just the direct formula. You can also do x greater than 87. So, notice what I have done here, greater than 87 is 1 minus fx of 87, right. So, this is probability that x is greater than 87 is probability of x, no I am sorry, this is 1 minus probability of x greater than 87 complement, right. You remember the complement, what is complement of that? That is x being less than or equal to 87. Right, x greater than 87 complement is x less than or equal to 87, and now we are ready to write it as fx of 87. So any interval, even if it is not within 2 points, it's only x greater than 87 or x less than 17, right, you can compute all of those using the CDF, okay. So in PMF terms, you would have added a bunch of probabilities, sum over all the values of k. In CDF, it is just the value of the CDF itself, okay. So that's how the interval calculation is done. Once again, I want to highlight 17 and 17.3, there is no difference, right. So given the CDF, it doesn't change. 87 and 87.4, there is no difference. You get the same value for the for everything, okay. All right. So this is computing probability of intervals using CDF. This is again a simple skill, and you should develop this given a description of the CDF. How do you find probabilities of the intervals? There are different types of intervals. I may include something, I may exclude something. You should know how to move around between these two. Maybe the intervals only go on the left side, only go on the right side, or between two values, maybe two different intervals. How do you do all that? You use the basic rules of probability, right? So the AND rule, OR rule, all of that just comes not rule. There's nothing new about it, but how to use the CDF for these calculations is very important, okay. We're going to revisit these calculations later on when we do some continuous look at this. But I want you to pick up the skill. This is important. You may have some assignments and tutorials on how to do these kind of calculations. Okay. So this is a good point to stop this lecture. In the subsequent lecture, we'll start looking at this larger alphabet case more closely and start drawing pictures of the CDF and see if we can make something, make this jump into the continuous world in an interesting way. Okay. Thank you.